3.7 Implicit Differentiation, Part 1. Your objective for this lesson is to differentiate implicitly. Okay, so implicit differentiation is how we find the slope when we cannot conveniently solve the equation to find the functions. So this is how we're going to find dy dx. You'll see right now. Okay, example 1. Find dy dx if y squared equals x. Now, this is different from other functions that we found the derivative of before because those have all been y equals. Here we don't have y equals. We have y squared equals. And your first instinct might be to just square root both sides, but that's not what you want to do. You know that if you take the square root of x, you're going to have a plus minus, and that's very messy. So let's use implicit differentiation here. Okay, so what we're going to do, we're going to differentiate both sides of the equation with respect to x. And we are going to treat y as a differentiable function of x and apply the chain rule. So we're going to differentiate both sides. So d dy of y squared is equal to d dx of x. So derivative, derivative. Now, I know the derivative of y squared is just going to be 2y. But I'm not just going to say 2y, I'm going to use the chain rule. So imagine that y is not just a y, maybe it's a bunch of other stuff. So I'm still going to say times the derivative, whatever that may be, with respect to x. And this is equal to, well, the derivative of x is just a 1 times d dx. Not dx, or dx dx. So 1 times whatever the derivative of x is. Okay. Now, this, you see, is kind of redundant. Dx over dx is just going to go away. So we're left with 2y dy dx equals 1. But what we want to find is dy dx. How do you get dy dx by itself? You divide both sides by 2y. Cancels. So we have dy dx equals 1 over 2y. And this is our derivative with respect to x. Example 2. Find the slope of the circle x squared plus y squared equals 25 at the point 3, -4. So the circle graph, oh, we can draw a circle, is like this. So if we were to write this as a function, you couldn't just write this as one function of x, because you know that every x would only have one y value, and this does not pass the vertical line test. So you could write this as y by itself, but it'd be a plus minus square root. We're going to use implicit differentiation. So d dx of x squared plus y squared equals d dx of 25. So since both sides are equal to each other, the derivatives are equal to each other, is what we're saying. And we're going to find the derivative of each term in the parentheses. So that's 2x plus 2y dy dx. We're not writing the dx dx because remember that's just going to cancel. So, but do include the dy dx. Equals the derivative of 25 is 0. Okay. Trying to get this by itself. I can't divide yet because I have that plus sign. So I'm going to subtract 2x from both sides. So we have 2y dy dx equals negative 2x. To get this by itself, we're going to divide by 2y. So dy dx equals negative 2x over 2y. But you know that you can cancel. So we get negative x over y. This is our derivative. But we want to know the slope at the point 3, negative 4. So we're going to plug those in. So negative 3 over negative 4. Is 3/4. So the slope at that point is 3/4. That wasn't so bad. You could have done this, again, with explicit differentiation, which is what we were doing before. If you broke that equation down, you got y by itself, plus minus square root, but it's a lot uglier. So, example 3. Show that the slope dy dx is defined at every point on the graph of 2y equals x squared plus sine y. So the first thing that we need to do to solve this is figure out dy dx. Okay, so what is it? You know that we are going to differentiate both sides of this equation. So we have d dx of 2y equals d dx x squared plus sine y. Okay, the derivative of 2y is 2 times dy dx. So that's your chain rule again. Derivative of x squared is 2x. Technically dx dx, but you don't write that. Plus the derivative of sine is cosine y. We have a y, so we're going to write dy dx. Now notice that you have this on two different sides of your equation. You want to corral them all onto one side. And I'm going to move this guy to the left side so that I can just leave the x alone. So let's subtract. These cancel. Okay, so we have 2 dy dx minus cosine y dy dx equals 2x. And since I do have this common term, I can factor that out. So this is 2 minus cosine y dy dx equals 2x. Last thing to get dy dx by itself is to divide by 2 minus cosine y. Bam. So dy dx is 2x over 2 minus cosine y. Okay, so this is our slope. This is our tangent line, this is our slope. And we're trying to show that the slope is defined at every point on the graph. So basically, we know this is going to be defined everywhere that the denominator is not equal to 0. So if this equals 0, let's figure out what that would be. So subtract 2 and then divide by 1. So cosine y would have to be a 2. But you know that cosine y is not going to be 2. If you look at its, oh gosh, that's a bad graph. If you look at its graph, that's still a bad graph. Okay. Let's rotate this a little bit. There we go. That's better. So the graph of cosine looks like this. And the highest it's going to go is 1. The lowest it's going to go is at y equals -1. So 2 is up here. Cosine y is never going to be 2. So this is never going to happen. Which means that we have nothing to worry about. Okay? So since cosine y is never 2, since cosine y is not equal to 2, ever, this derivative will be defined at every point xy. Okay. So this is a summary of how we differentiate implicitly. This is on page 151 in your book. This is word for word out of your book. So step 1, differentiate both sides of the equation with respect to x. So that is this step here, the d dx that you put in each side of the equation. Step 2, collect the terms with dy dx on one side of the equation. So again, going back, that's when we moved the cosine y dy dx to the other side so we could get them all together. Step 3, factor out dy dx. That was right here. Okay, so dy dx came out, everyone else stayed together. And step 4, your last step, solve for dy dx. So this is your division. Okay. Example 4. Find the tangent and normal to the ellipse x squared minus xy plus y squared equals 7 at the point -1, 2. So if we're going to find the tangent and normal, we need to find the derivative to get the slope. Okay? So what I'm going to do is, step 1, differentiate both sides of the equation with respect to x. So d dx of this side equals d dx of this side. And I can actually write this out also. This is one of your derivative rules. So d dx of x squared. So I can just basically break this up. Minus d dx of xy plus d dx of y squared equals d dx of 7. Okay, so this is the same thing, just written a little bit differently. I'm leaving that behind again. Okay, so let's get to it. The derivative of x squared, you know, is 2x. I'm not writing dx, that is redundant. Minus. Okay, so we have a little product rule here. So this is multiplication, so we have the product rule. Remember, u dv plus v du. So we have then x is u, derivative of y is dy dx, plus y, the derivative of x is dx dx, which we've already established we don't need. Okay. Plus, derivative of y squared is 2y dy dx. Okay. Equals, derivative of 7 is 0. Okay, simplifying. We have 2x minus x dy dx minus y plus 2y dy dx equals 0. Okay, so now that I'm simplified, I have everyone with their dy's and dx's. I'm going to find my dy dx terms, which are here and here. You had the whole thing. And I'm going to isolate those. So I'm going to move everything that I haven't highlighted to the other side of the equation now. So subtract 2x and add y, both sides of the equation. So these go away, and we have negative x dy dx plus 2y dy dx equals negative 2x plus y. Okay, so that was step 2. Now I need to do step 3, which is factor out dy dx. So negative x plus 2y times dy dx. Okay, equals negative 2x plus y. To get this by itself, I need to divide by negative x plus 2y, both sides. Gone. So we have dy dx equals negative 2x plus y for negative x plus 2y. You might also write this, if you don't want to have the negatives out in front, you could say y minus 2x, 2y minus x. That would be fine. Okay, so these are the same thing. But this doesn't answer the question. I know that was a lot of work. But what we want to do is find the tangent and normal to the ellipse. So we're looking for 2 equations. And I don't just want 2 equations. I want to have an actual number for the slope. So right now I have an equation for the slope. But I need to plug in my x and my y to get a slope for the tan line. So let me do that first. So I'm going to do this in blue. My point was at -1, 2. So my slope at that point is 2 minus 2 times -1, so I'm using this equation here, over, so 2 times 2 minus -1. Okay, so this is 2 plus 2 over 4 plus 1, which is 4/5. So this is the slope of the tan line. Okay, and let's find the equation of the tan line. So we have y minus y1 equals mx minus x1, which gives us y minus y1 is 2 equals 4/5 x plus 1. Okay. Distribute that 4/5, so we have 4/5 x plus 4/5. It's y minus 2. I'm going to add 2 to both sides, and 2 is really equal to 10 over 5. So I'm going to add 10/5 to both sides. So plus 10/5 plus 10/5, same idea. So y equals 4/5 x plus 14/5. Okay, so this is the tangent line. This is your equation of the tangent line. Okay, but we also need to find the normal line. You know that the normal is perpendicular to the tan line. So we're going to take 4/5 and flip it over 5/4 and change the sign, -5/4. And our equation, we use the same basic setup. So we have y minus 2 equals, because it's at the same point, -5/4 x plus 1. Okay, so we have -5/4 x minus 5/4 because we distributed that to our parentheses. And 2 is equal to 8/4. I want the same denominator so I can add it to this. So I'm going to add 8/4 to both sides. And y equals -5/4 x plus 3/4. So this is the equation to the normal line. Okay. And it looks like that is it for 3.7 part 1.